Hi, welcome back. I've been watching Julian Elet's video on NeoPixels, where we run them from a PIC microcontroller by bit banging the port and shifting out bits into the NeoPixel registers. So, NeoPixels, what are those? Well, those are like another LED like you used to. These are RGB LEDs. You can also get with a white also. If you go down here, you have one with white. If you look closely at them, you can see that these has 3 LEDs, red, green and blue. And there's a chip. So there's a chip inside. And this chip has a shift register. And when you have a shift register, you can then connect all these LEDs in series. So when you push data in, for every bit you push in, there will be a bit coming out of the register in the other end. So what you have to do then is to push it through the whole register. So if you have 16 LEDs, you have to push all the data through the first register, and then the last piece of data will then stay in the first one. So yeah, so that's interesting. So in this die shot you can see the 3 drivers for the LEDs. They have some pulse width modulation. I don't know where in this diagram you can see that. You have data in and out up here, I think, or here. I'm not. Okay, I think it may be here. Not sure, but anyway, what you can see is this is like a register. It comes down here, and these are individual bits, I think, and there are 24 of them. It goes like this, and eventually they end up driving the intensity of these outputs. Yeah, it's about bought a NeoPixel ring 16 times 5050 RGB LED with integrated drivers. They are from Adafruit, and I bought them here in Oslo at a place called Shell.com. So the main reason for doing this video was to try and make like a sparkling effect on the shift register. So therefore I need some random function. And line or feedback shift register are such functions. Here I am showing the shift register out on port A, B and C. And not all of these LEDs are lighting. That's because some are used, like the first one is used for the NeoPixel ring output. And you can see when data is shifting down the shift register, it's not. You can see a pattern, so it's not really that great a random number. And also I haven't coded this correctly, so you can see that the pixels are indicated for whatever number we get on the 4 first bits here. So what we can do is shift twice and then read a number. So, and then you can improve the random number you get from the shift register. However, when you do that, you are trading off half the sequence length. But it's a 24-bit register, so it's great. Okay, I have updated the code with a shift register that shifts twice before it updates the output and the NeoPixel ring. You can still see some running lights. Naturally, the data will travel down here, and then if we just do it twice, shift it twice, data will jump from here to here. Super easy to make. The theory behind them is very hard. I don't actually understand it. So, but from this theory, it's about prime numbers and Galois fields, and then the thing is that with these polynomials, you get a random sequence when you run the formula on it. When you take the algorithm, is that in hardware this is super easy to do. You shift left and then you soar something you call taps. So you have a register that's like a series of shift registers, like this one. I made this one so you can see it's running. I can stop it. As long as the shift registers are greater than 0, it will run, I think, because now I have set all of them to 0. So if I start it, you can see that it gets stuck. So that's one thing about this LFSR. They need a number greater than 1, I think. There might be some numbers that it makes it go stuck, I'm not sure. So now I put a 1 in here, and you can see it starts running right away. So yeah, really cool. So how do you build one? Here you have a primitive polynomial x8, 4, 3, 2, 1. You take these, which are in the middle of this polynomial, so that's 4, 3, 2, and therefore you put a tap on 4, 3, and 2. So that's how you build it. It's very simple like that. So let's look at the code. Now I've showed you videos, how it's working, and now let's start with the code. UK, I watched his video and I saw that when he used a variable, he then used the EQ directive, so then you get a constant. But when you start deeper, they go away. So I have to reserve them. So if I reserve them, like you do in C, you don't say exactly where in memory they will be put. Just say you want to reserve memory for them. Set of the oscillator to internal oscillator 8 MHz. Then I tune it up to max, so we can shift the frequency up a little bit. If I don't do that, you can see in the video now that what happens. If you don't move a number into the shift register, the LFSR will never run. So if it's 0, it won't run. LEDs that are not going to be lit. So I take the first 4 bits of the whole register. That's what I'm doing here. And then I put it into delay. So the first part of the loop will just write 0 pixels, if you can call it that, black pixels. So the loop is such that the delay is decremented, and when it's empty or 0, this instruction will skip the go to loop, which is up here. And then it will write the pixel, and what it does then is to fill in the rest of the pixels with nothing or black. Or yeah. So, and here you see the loop again, fill rest. So what is write L then? Let's jump down to that. Yeah, that's the same as Julian had. So you set the bit, and then you clear the bit, and then you do nope. So therefore I get under 500 nanoseconds. Actually I get right under, so it's not there's not much margin here because I'm running at 8 MHz, and then you get 500, in theory I get 500 nanosecond instruction period. Is that the correct way of saying it? And if I want to write a high, I will put a no operation such that I get more than 500 nanosecond. I'm calling this function 4 times, so I shift the register 4 times before I do anything. So, and then I call delay. I set up the delay variable again, and then I just loop in here just to sort of keep it busy, so we can actually see something happening. This is the subroutine, and what it does, it reads the taps. Well, when I want to rotate the shift register at the end, That's basically what you do. You soar and rotate. That's all you do. But to get that soaring, I needed to do some stuff to get it done. So then you're just rotating using carry. So maybe 16 instruction cycles. It's not very long. But if I had been smart and done my homework before I started this, I would have used or made a internal type, because then you don't have to do all this rotating, and then you just set up a mask. I can show you that. This is an internal type, and what you do is very easy. Let's see if we can zoom in. So this is assembly code, but it's a bit difficult to read. Maybe C is better. So what you do is they want a random number. They store the first bit of the shift register. Okay. Then they rotate right. Actually, they are moving it in the opposite direction that I'm moving it for some reason. Because when I'm moving right, then okay. Actually, I'm running the register in the reverse, I think. Anyway, I think that's not a good idea. But how are you going to utilize carry then? So I think I will run it the other way. Yeah. So they shift the register to the right, and then they take this something called polynomial mask and soar it with the shift register. So that's very much shorter code. You can see also there it's much shorter than I had.
What do you think? Was that better? So now it fills all the pixels, and the shift register is skipping 4 bits at a time, or shifts 4 at a time, so get a bit more random number. So I don't know. It's not very glittery yet, so maybe if we run it faster. So it's running faster. Let's try a little bit faster than this. So programming it. See. Kind of cool.
I'm going to make the internal version, but I'm not going to film all the coding, maybe, because it will get very boring, I think. So I made a LFSR external. I will make another called LFSR internal, and we'll go from there. So then finally return. So I will film some of the debugging, but not everything.
Okay, I implemented a 16-bit register, and now using Galois style, internal style, and I can't get it to work properly, so I wonder what I'm doing wrong. And why are all of these 0 all the time? So I'll have to figure out why. Okay, I think I found out why, so let's have a look at the screen. Ooh, this looks much better. 16 bits.
Yay, it's working. So here's the code. I have selected these tabs, and what I did wrong was, okay, first of all, this is in Galois LFSR, or an internal, what's also called. We had an external Fibonacci type A Fibonacci type is also called a simple shift register. That's what I had. I just had a shift register that ran whatever came in on the feedback path, just pass through it. So if you look here, you can see that whatever came in on the shift register just passed through it, and what was actually fed in was had sort of the entropy or the sequence changing via this external. So for an Galois or implementation of LFSR or internal, we have the SOR gates in the middle here, so therefore the sequence is changing all the time. Looks more like a Christmas tree, blinking Christmas tree, so that's nice. So yeah, the thing is that when I do this Galois instead of Fibonacci, I have to change the sequence. So every feedback tap, this is also tap actually, the one from the output, and also the tap here, you can see from this register is also tap. So the sequence is reversed in comparison to the LFSR Fibonacci. So yeah, enough about that. So that's what I did wrong. So when it says 16, 15, 13, 4, that's 16, 15, 14, 13, and then 7, 6, 5, 4. Yeah, so there you have all your taps. So, and you can also see in this code, if I we can debug it. So let's start a debugger. We can watch our variables. We'll not have so much on the screen then, but that's okay. So we can see that this is the shift register. We can ignore the high byte because it's not in use because it's 16-bit. It's just these ones. So clear flag, rotate. So that's really great. You just rotate. So and here we have something called branch carry. And branch carry. If the carry is set, okay, it's open status, you can see its status is 0, then this will not branch. So that means it will call 2 ports and then return. So if the last bit here was not 0, it won't do anything. So, and if you go back, you can see that it makes sense, sort of. If the last one is 0, then you have 0 on all the feedbacks here, and 0 going into a SOR gate will just act like a pass-through. So how can I say that? Well, take a look at this for SOR. Well, if A is the feedback, if A is 0, then B equals the output. You can see that B equals 0, Q equals 0. B equals 1, Q equals 1. Now it's different if the feedback A is 1, then you can see there's an inversion. So if we go back, we can see that it's no point of doing any masking here. It's called mask. I forgot to say that actually. Mask, high byte, and a mask, low byte, and here you can see that they are stored in. So yeah, let's continue. Yeah, we saw the branching did not branch. So if you don't know assembly or coding, the branching means that you jump in the code. So the character flag was 0, so it just calls the port and then it returns. So let's just play again to break it up here again. So play. Okay, let's just hit play until we get that one over here. Down, 2, 3. Okay, now we have this one out here. What happens now is that when we run the shifting of the shift register here, we can now see that we have a carry, and this branching will now have a carry. So let's see what happens. It branches. Look, it jumped over that return. So now we will start masking. So first we put the mask into W. There we go, WREG. Now we saw that mask with the LSR plus 1. So then everything that's 0 will stay the same in this LSR plus 1, and everything which is 1 will then change. So let's see. Yep, everything was the same except that one which changed. So yeah, so I won't talk so much more about that. That's very easy. So, and for the low part. So yeah, so if I click this repeatedly, you can see that this register only scrolls from right to left, and then if you get a 1, you get some different pattern. Yeah, so I really like that. And
Okay, so the last thing I did was to make the 60-bit LFSR and the 32 or 24-bit LFSR, and I sort them together, and I take only the 4 first bits. So you can see, yeah, I think it's a little bit, look a bit more random now. So maybe it's more likely that it jumps around and it goes to the next one. Yeah, not sure what to do about that, so it's not that easy.